Regarding the quiz, I'll get them graded as soon as possible, and I'll post your grades onto Canvas. You can check just by looking at the grades section on Canvas. If you want to see what questions you got wrong on the quiz, you have to come see me during office hours, okay? I don't actually return the quizzes. I hang on to them myself, just because I do reuse a lot of the questions from quarter to quarter, so I don't like to have the official quizzes floating around. I do feel like the practice quizzes are representative of the actual quiz, so because the practice quizzes are made available to you, I don't think I'm depriving you of a study resource either. So if you want to see what questions you actually got wrong, just come during office hours. I ask that you send me an email, okay? So I'll write this. If you want to see your quiz, what's going on here? Okay, something funny is going on with the screen here. I'll have to figure this out in a moment. If you want to see what's wrong with your quiz, send me an email, and then okay, this is much better. Okay, so I'll write that. If you wish to see your actual quiz, send me an email, and then and come to office hours. Okay, and that way I don't have to fish out your. I don't have to bring the whole stack each week, and then and I'll have your quiz fished out of the pile. Yeah, question.
Did you say your office hours were before 45 minutes?
Correct. So I'll generally get here around 6:15, and I'll just wait, and if no one has any questions, I'll just be standing here probably reading articles online. But if you got questions, I'm happy to answer them. If you want to look at your quiz, I'll answer them too.
Because just so that you know, the syllabus says Tuesdays from 6:15.
Oh, okay. That's a mistake. It's Mondays. Okay. Oh, other major mistake in the syllabus. Okay, so please write this. The date of the midterm exam is the 6th week of class, okay? But I counted the calendar wrong, okay? That's Monday, October 24, okay? In the first thing it said October 31, so I sincerely apologize. That was a mistake. The 6th week of class is the midterm. That's Monday, October 24, okay? So thank you for catching that and bringing that to my attention. Okay. So again, I'll get them graded. I'll post your quiz scores online, and then if you want to see it, send me an email. Otherwise, that's that. Okay. All right. We good? Okay. All right. Okay. So. Okay, so just a brief recap of last week. Okay, so we said last week, we said that statistics allows us to make conclusions from our data. Okay, and we looked at just a few ways to summarize categorical data. Okay. can summarize and describe categorical data with frequency tables. Okay. What's the other kind of table that we have? Two-way tables. And then as far as displaying, what do we use to display categorical data? A bar chart, right? Exactly. Or a pie chart, which we prefer not to use, okay? And so this is all just part of describing our data, okay? So this all fits under this broad category of descriptive statistics. Okay. And so today we will cover more descriptive statistics, and specifically descriptive statistics for numeric data. Okay, so let's flip the page here. Okay, and so today more descriptive statistics, and we will learn descriptive statistics for numeric data. Okay, we'll start with some displays, ways to display numeric data. Okay, and these will include the dot plot, a histogram, and a box plot. Okay, and then we'll also have numeric summaries. And these include things like the mean and standard deviation and variance. Okay, we'll also have the median and interquartile range and things like that. Interquartile range is also abbreviated IQR. Okay. I should just take a moment right here and just check with those seated in the back that you guys can read okay. Everything's good. And of course, if you have any trouble seeing what's on the screen, I invite you guys to move forward. Yes, question.
Sorry, I can see, but I just don't know what it says after standard deviation
And variance. Yeah, somehow a little something. What is this? It's variance. Okay. Okay, so let's talk about each of these things, all right? And so this is, we're still in this general, I guess, part of statistics where we're just learning how to describe the data, okay? So last week we learned how to describe categorical data, and this week we'll learn how to describe numeric data. All right, so let me just copy some numbers out of our textbook. So this is on page 39 of our textbook. Okay, and the data we have here is the number of goals scored by first year NCAA female soccer players in Division III. Okay, so it's very, very specific, but okay, so this is a number of goals scored by female Division III soccer players. Okay, and we want to be able to summarize what we have here. Okay, and so this is our data. Okay, and so it's clearly numeric data because it tells us the number of how many goals someone scored, and we can display this with a dot plot. Okay, and so to create a dot plot, we're going to start off with the pieces of a dot plot will be kind of this number line. Okay, and we would label values on the number line 9, 10, 11, 12, etc., etc., etc. Okay, and then we would put one dot for each value represented in our sample of data. Okay, so we would see this person who scored 9 goals, and we would put a single dot at 9. Okay, and then we would see these 4 people. There's 4 people who scored 11 goals. There's no one who scored 10 goals, so there's no dots there. And at 11, we would put 1 dot, 2 dots, 3. We would put 4 dots at 11 to represent these 4 people who each scored 11 goals. Is that clear? And then how many dots would I have at 12? 1. Okay. And then when I get over to 13, I would have 5, right? Okay, so I'm going to go ahead and cheat and take a shortcut and copy this dot plot, which appears in our textbook. But I think you guys get the idea on, I hope, get the idea on how to make a dot plot. All right. So this one, they didn't number every single thing, but we can see that it pretty much has the same information that I was doing. Okay, is that all right? Okay, so this is the dot plot where they completed all of that, filling all of that out. Okay, so we have, so again, it's very important that you have the number line, and that creates kind of the arrangement here. Okay, and then so we can look at the dot plot. Okay. To get a sense of, the kind of the typical number of goals scored, okay, or to get a sense of the distribution of these values. Okay, we can look at the dot plot to get a sense of the distribution of values. Okay, so if we look at this, what seems to be kind of like a typical number of goals that someone might score?
15.
Something around 15, right? This seems to be kind of typical. So, quote unquote, typical is, something around 15. Okay, maybe a little bit more, maybe a little bit less. But we have this kind of we get a sense that this is kind of, this zone right here, this is kind of like what your average number of goals is, something like that, okay? Just by looking at that, okay? And then we can see that, this 35, this is rather unusual, right? Okay, and we notice that 35 is unusually high, okay? yeah, so. Okay, and so, you know, later on we'll learn terms for these types of features. We might call something that's unusually high or unusually low an outlier. But at this point, we're just looking and we go, wow, there's quite a gap between 35 and the next highest number. Okay. All right, so that's a dot plot. Okay. Is that good? Okay. We can take our data. All right. Let me. So we'll take our, here's the dot plot again. Let me also just kind of copy these values again. Okay, we can take this and we can, instead of having dots, we can draw little bars. Okay, and this seems kind of silly, but we could do it, okay? And so I've got I got a bar at 10, and then 9, 10, 11, 12, 13, 14, 15. And we can basically represent all of this, and instead of dots, I will make bars, and we'll have kind of a thing to have them represent the counts up on the side. And so I've got one bar at 9, okay, or one dot at 9, and so I'm going to create a bar for 9, okay? And then I would come over here and then I would look at 11 and I would say, oh, here we got 4 at 11, okay? And then 1 at 12, and then we would go to 13 and we would have, whoops, 5 of them, 5 values at 13, and I don't really feel like doing all of this, but okay, and then I'll just write et cetera, et cetera, et cetera. Okay, but I'm hoping you guys get the idea here, right? So here, basically, I'm just, instead of dots, we're using bars. Okay. Okay, and then you know.
This is a histogram?
Yeah, this thing would be called a histogram. So if you, instead of dots, you use bars, this chart is called a histogram. All right. So then you might ask, well, why would I bother? Like, if I've got a dot plot, why would I bother making a histogram? Or if I've got a histogram, why would I ever make a dot plot or something? Okay, these are valid questions, and I'll try to. And then I don't know. We might color them in to make it look fancy or something. Okay, and I just want to make it clear that this, as it stands, it's incomplete because we should have more bars over here, right? Nobody is going to ask me like, what happened to these dots that were at 20 and things like that? Okay, so just in the interest of time, we're cutting them out. So this is a histogram. We've got bars instead of dots. Okay. Another thing we can do is we can create bins. Okay. With histograms, we can bin our goals. Okay.
What does that mean, to bin?
I will explain. Okay. With histograms, we can bin our data. Okay. And so over here, the person who scored 9 gets a bar at 9, okay? And then these people who scored 11, they get their own bar represented at 11, and this person who scored 12 goals, this person gets their own bar at 12, and the people who scored 13, they get their own bar at 13. Does that make sense? Okay, or we see that. So when we bin them, okay, we can create ranges, okay? So we can say number of goals, and we can bin them together. We can say if you scored 9, 10, or 11 goals, you're going to be in this bin, okay? And then so that bin would just be the 9 to 11 bin, okay? And then we could do 12, 13, or 14. So this would be the 12 to 14, and so on and so forth. It would be 15 through 17, 18 through what? 20, okay? 21 through 23, 24 through 26, 27 through,
Et cetera, et cetera, et cetera.
yeah, et cetera, et cetera, et cetera. I just want to get to that last one.
But just 3 numbers, right?
In this case, it's 3 numbers, but really, when you create the bins, they can be any bin size you want, okay? If you want to put 10 numbers in a bin, you can put 10 numbers in a bin. It's just every bin should have 10 numbers. You don't want to do one bin has 3 numbers and another bin has 7 numbers, okay? That's not allowed, okay? So make sure you put the same number of values, or same number, I guess, yeah, the same number of values in each bin, and then you count the frequency, right? So we go, okay, how many data points are between between 9 and 11, and we go, oh, there's 9, 11, 11, 11, 11. We have a total of 5 values in 9 through 11, okay? And then you say, okay, what about 12 through 14? And we count all of these, and we go 1, 2, 3, 4, 5, 6, 7, 8, 9. We go, oh, we've got 9 values here, okay?
What are the 9 values?
So here I'm counting right here, 12, 13. So I've got this 12, the 13s, and the 14s. If I count how many values, how many numbers I've got here, how many data points, I've got 9 data points in my data that are 12, 13, or 14.
All right.
Okay? All right, what about 15 through 17? How many do I have there? I've got 6, okay? And then we keep going, and we've got 6 that are between 18 and 20. And then at 21, we have 1, and then all of these we have 0. And then finally we get 1 at 35, okay? Okay, and so we have this now. And then we can graph this, okay? And actually, the book does this for us. Let me cheat here and copy this image. Okay, and that's this exact. Whoops. Okay, so this histogram we can see. Okay, between 9 up to but not including 12, so 9 through 11 we have 5. Okay, 12, 13, 14 we have 9. At 15, 16, 17 we have 6. At 18, 19, 20 we also have 6. Okay. It's customary to just kind of draw the left, write the number for the left boundary of the bar. Okay, so rather than trying to say like 9, 10, 11, you just write 9, and then over here you write 12, and it's assumed that the bar starting at 9 represents everything from 9 up to but not including 12. Okay. All right, is that okay? So here we've created a histogram. This is also a histogram. Okay, but here our bins have a width of 3, okay? Meaning each bar represents 3 different values. Whereas over here, our bin width was 1. Each bar represents only 1 unique value, okay? And we count how many numbers in the data set have that value. Yes?
Why would it be more advantageous or disadvantageous to use the bin?
So why would we want to do binning? Okay. All right. So let's say, well, because as humans, we kind of bin already, okay? Whether you realize it or not, we bin, okay? And this is an automatic thing. If I asked you how tall you are, okay, or how much do you weigh, most likely you're going to say I am something like, you know, you're gonna say I'm 5'10" or I'm 5'7". You're gonna round off to the nearest whole inch, okay? But truly, if we put you against the wall and we measured your height, it's not like your human height is limited to 1 inch increments, okay? So you might actually be 5'7" and 1/4 inches. You might be 5'6" and 3/4 inches or something like that. And so if we measured, you know, everyone to the nearest 1/4 inch or whatever, we would have all these different values, and then our dot plot or histogram would have all these tiny, very thin things, okay? Same thing with weight, okay? You might say, I weigh 100. If we asked you, how much do you weigh, you're probably going to round to the nearest 5 pounds, okay? I mean, some of you might say, I weigh exactly 163 pounds or something like that, or 122, but most of the time people round off kind of to the nearest 5 pounds, and that's just to kind of avoid having to deal with too many individual values, okay? So that's why we bin, and we kind of naturally do this. Especially with large data sets, we might even bin to the nearest 10 or 100 or something like that. Yeah?
Will we always be provided that information, like, you know, how there's the 9?
You mean the individual values?
Yeah, and then, like, my question is, like, you see between the 9 through the 12 that there's a frequency of 5, but how do you know that there's 4 11s?
Yeah, you don't. So the problem with binning is you lose that detail, okay? You've binned all of these people together, and the people, you know, if we bin people, if we say, how much do you weigh? And then we say, okay, well, these are the people who weigh between 100 and 129 pounds, okay? You don't know specifics, and people might be upset, and they might be like, I only weigh 120, and I'm put in the same category as this person who weighs 129. You know, that could happen, but there's a trade-off, right? Do you want to know every single value? If you want to know every single value, just look at the raw data, right? These, we look at graphic displays to make our life easier, so we kind of get the general idea, okay? General idea of the data. Here we can still kind of see most of the values. The typical is something around 15-ish, even though you lose the individual things. So the dot plot preserves the individual values, okay? You can imagine if we had a very large data set with like 1,000 data points, the dot plot would have 1,000 dots, and that might be uncomfortable for our eyes to look at, okay? And so in that case, histograms will do a better job, yeah.
So you're saying it's disadvantageous to know every single value then?
It's not disadvantageous. It's just sometimes you don't.
Too difficult? Too much information?
It depends. Okay, the answer is always it depends. In certain contexts, you don't want to know every individual value. In other contexts, the individual values matter, right? So it depends. Okay. Yes. Question.
I'm still a little fuzzy on the definition of a histogram and like a histogram as opposed to a what? A dot plot?
Yeah. So both dot plots and histograms are ways to display numeric data, okay? So if you think of what numeric data is, at some level, it's just a bunch of numeric values. Here we have 9, 11, 11, 11, 12, whatever, okay? We have a bunch of numeric values. Rather than just listing them off like this, which is a perfectly valid way to showcase the data, okay? There's nothing wrong with showcasing the data like this, except perhaps we don't want to look at the numbers this way, right? So one way to display the data is to turn each of these values into dots, okay? And if you have, you know, something like less than 50 or even 100 dots, it's not so terrible to look at, okay? When you're getting large numbers, you know, in multiple hundreds or thousands, okay? We might prefer to have histograms where we've binned or we've grouped some of these values together, so we don't have to worry about it, right? Because, you know, let's say we wanted to know how much people, you know, annual incomes, right? Okay, when you file your taxes, they round off to the nearest whole dollar, okay? If we had a dot plot, it would have a dot for someone who made $33,056, and then it would have and it would have a stack of people who made exactly $33,056. But then if somebody else made $33,057, they would have a different dot in a different column and have a different thing. And we can see, like, this kind of display is not going to be very fun for us to look at, right? So it might make more sense to just say, okay, everybody who made between $30,000 and $35,000, group them all together, or something like that, okay? Huh? For binning, yeah. And then, so, and histograms, if you're going to do binning, you've got to use a histogram, okay? You can't, it's not a dot plot if you're binning, okay? Question?
Yeah, can you give me a precise definition of what a histogram is? I get the idea. I just want it in concrete, you know, in concrete form.
A histogram is a way to display numeric data using bars. I don't know. It's, you know, you got a bar chart, right? For categorical data with a histogram, it's the same thing. You're representing the data using bars, okay? But the important thing is, on the bar chart with categorical data, you could rearrange the bars, okay? With a histogram, you cannot rearrange the bars because they're tied to the number line, okay? So maybe, I mean, that might be worth putting, okay? So I'll just write this. So histogram versus bar chart, because I think some people get these mixed up, okay? Okay, histogram is for numeric data. Bar chart for categorical. And then the important difference is that the order of the bars is tied to the number line, okay? Okay, so 5 is always less than 6, which is always less than 7, and the bars have to be in that order, okay? Whereas with categorical data, the order of the bars is arbitrary. Whatever you want to put in alphabetical order, that's fine. You want to put them in some other order, that's fine, okay? The order of bars is arbitrary. Okay, stylistically, and this one doesn't matter so much. With a histogram, we generally have no gaps between bars. This does not affect the interpretation of a histogram, but generally when we create a histogram, there's no gaps between the bars. And then with bar charts, as far as style goes, sometimes we usually put gaps between the bars. Oh, okay, so here's a good, maybe a good case where we can compare the dot plot versus histogram, and then and we can see where we have this, okay. I'll give it its own slide. So this is the same data, okay, and up top we have a dot plot, and on the bottom we have a histogram. I'm sorry? Okay, and so here we are looking at 184 different schools, so our data. Here we have 184 law schools, And so in this dot plot, we have 184 dots, okay? And what we did is we looked at each law school and we said, okay, of your graduates, what percentage passed the bar exam, right? So if you want to practice law, you got to pass the bar exam, okay? So this is what percentage passed the bar, okay? And so, you know, we have a lot of schools where, you know, 80%, 90%, you know, over 90% pass the bar, okay? And then, you know, we have some schools with lower than 80%, you know, 60%, and this is like a terrible school that has, what, like a 30% pass rate, okay? That's not something that they would advertise, but maybe it's like...
It's important for statistics, though.
Well, I mean, they might say, you know, we'll accept anybody type of thing. That's the way some schools market themselves, right? Okay, and so so here we can see this is the histogram has created bins of basically width 10. You know, even though these numbers aren't there, we've got basically 80 through 89, 90 through 99, or 100, things like that. Okay, and we've binned them together. And so this is the same data, and we've got the dot plot and we've got the histogram here. Okay. So what would we say is kind of like the typical pass rate? Looking at this. Yeah. So if we had to pick a single value, probably something around 85-ish, something around here. Okay, maybe. So this might be kind of our typical-ish value. Typical. So we might say schools that have over an 85% pass rate, that's, you know, better than average. Schools that have lower than an 85% pass rate, that's a little bit worse than average, or something like that. Okay, we can. So we have the histogram where we've binned the values together. We can even further just simplify. Let's simplify the shape of our data with something like this. Okay, and so this curve, this is a curve to kind of represent the shape of our data. Okay, and does that feel okay? All right, and we would call this thing, the way we would describe it, we would say the shape is left skewed. Okay, meaning there's a tail. This thing is called the tail. Tail points to the left. You can think of the tail as kind of the pointy end. Or if you're going to skewer something, you would use the pointy end, okay? And then we would also call it unimodal. Unimodal means one mode, or one peak, one hilltop, okay? One peak, all right. And so to think of, you know, so if we're saying something is left skewed, okay, the idea here would be that kind of your typical value, or a lot of the values, your typical value and the kind of your bulk of values are going to be generally on the high end of the scale, okay? And that, you know, the highest value you can achieve for your pass rate if you're a law school is 100%, right? You're not going to get over 100% pass rate. So that's probably, you know, your elite law schools like Harvard and Yale or something like that, where I would imagine something very close to 100% are passing, okay? And so, you know, that would be the highest that we can achieve, and the typical value is fairly close to the high end, okay? Typical value and bulk of points are closer to the high end. High end being, you know, on the grand scheme of things, okay? You have no outliers on the extreme high side, okay? No outliers on the high side or above a certain point, okay? But you do have kind of some outliers or a few extreme points on the low end, okay? Is that okay? So, you know, this school with, you know, like a 20-something% pass rate, that's extremely low, okay? And that would be considered unusually low, and that would be an outlier on the low end. Okay, and that's something that's an indicator of being left skewed. Yeah, question?
Explain me the importance of the tail in this, is that just interpreting the left?
So the tail, yeah, the tail means you've got values. We have values on this low end, right? Mm-hmm. So this, you know, this part over here, this is kind of like the tail. Not fail, although that's also true. But so this would be the tail, okay? And these are values that exist, not a lot, but values that exist, okay? And we have these kind of these more rare values on the low end, but not on the high end, okay? And so this would be something of a tail here, okay? And because the tail's on the left, we call this left skewed. Is this okay? So I'm going to just kind of draw something. So if we have something shaped like this would be...
That's the tail where you ended, right?
Yeah, this thing would be called right skewed, okay? So you have some values on the high side. So it's just kind of flipped around from left skewed. You have some values that are on the extreme high side, not too many, and then on the low side you don't have any here. Okay, so that would be right skewed. Something like this.
So no matter what, you start from left to right. Right?
No, I mean that's just the way because I'm used to writing English from left to right. I have a tendency to draw my lines from left to right, but just this, I mean, we're just representing the data here, okay? All right, so here we've got, so this would be right skewed, so maybe an example of something that's right skewed, maybe human weight. Okay, so if we think of like, you know, even maybe in the United States, okay? So, I don't know, we'll just say if we look at average adult weight in the US, okay? You know, probably the bulk of people, adults in the United States, will probably weigh something between, you know, 100 and 250 pounds or something like that, okay? And, you know, maybe most around 170 or something, okay? If you go much lower than 100, you're not going to have very many adults weighing that much less than 100 pounds, okay? And on the other hand, you know, are there people who weigh, you know, 400 pounds, you know, things like that? Yeah. maybe not too many, but you have people that weigh a lot. Okay, and so if we just say kind of your quote typical weight, whatever typical might be, let's just say typical something like 170 pounds or something like that. Okay, if someone weighs let's say 400 pounds, okay, or even 350, okay, 350 is 180 pounds above your typical or above your average weight, whatever that, it's kind of an arbitrary number, okay? But if you go, so this is 180 pounds above average. If we want 180 pounds below average, we would be at negative 10 pounds. It's not even possible to weigh negative 10 pounds, okay? And so, you're gonna have kind of the bulk in kind of this middle-ish region, and then, but you're gonna have some extreme points on the high end because there's not like a hard limit for the absolute most a human can weigh. But on the low side, you do have some people who weigh very little, but there is a hard limit. You certainly cannot weigh less than 0, okay? And so you're going to have something that's right skewed. Okay, symmetric. On the other hand, you got tails in both directions, right? So you have tails on both sides. And this would be something a little bit more closer to human height. Human height is closer to being symmetric, okay? So, just for simplicity, maybe we'll pick, one of the genders, and we'll say, in the U.S., the average female is something around 5'4", 5'5", okay? And you do have some women who are very tall, okay? But, the farther you get, if you go over 6 feet, you're going to have fewer and fewer and fewer women who are, that much taller than 6 feet, okay? But on the flip side, if you go, lower than like 4.5 feet or something like that, you're going to have fewer and fewer women who are much shorter than that, okay? So, kind of the bulk of women are probably between 4'10" and 5'10"-ish, okay? And then as you get further and further away, you're going to have fewer people out here and fewer people on the extreme high or in the extreme low. Question?
Yeah, can you have tails on more than two more than 2 parts on a
So tail is really like the extreme high or the extreme low. So I don't, I don't think you're going to have tails more than, you can only have at most 2 tails. Okay? Either tail to the right or tail to the left, maybe tail on both sides. All right. Is this good? Okay, let's have kind of a question for, I don't know, the cards. So think of annual income in the United States. Annual household income. In the USA, okay? And so think, is this skewed left, skewed right, or symmetric? And we'll say green if you think it's skewed left, pink if you think it's skewed right, and we'll say orange for symmetric. Okay, so pick out a card that you think. So think about annual household income in the U.S. Skewed left, skewed right, symmetric. Think about that. Okay. Think about what it means to be skewed left, or what it means to be skewed right, or what it means to be symmetric, and think of annual household income in the U.S. Okay, and see if you can pick a pick a card out for yourself. Okay. All right, and then I would say now turn to a neighbor, turn to someone sitting near you, and discuss the answer you chose. See if you can convince them one way or another why you picked that. So you might want to think about like what is typical. Do people make more or less than typical? Can you go extremes on one side or the other? Or both sides? Okay, all right, so let's get your, so if you want to change your answer, you can change your answer. And all right, let's go ahead and hold up the cards. Let's see what we think. Okay, so we got a bunch of pinks, we got a bunch of orange, we have a few greens. Okay, so the answer is household income in the USA is skewed right. All right, let's discuss this. Okay, so I'm gonna think of what's kind of your typical annual income. Okay, well, just give me a number.
500,000.
Typical annual household income. All right, let's say okay, we'll say 50,000 a year. Okay, I don't know. Okay, I think that's 50 to 60,000. That's kind of your median household income. Okay, poverty line is something around 25,000 or a little bit lower than that, or something around there. Okay, so that's typical, right? And then what's like the lowest possible value for household income? 0, right? That would be the absolute lowest as far as income goes. Okay, what's the highest? Huh? Yeah, it's unbounded, right? Okay, there's no bound. Like, are there people who make $1 million a year? Are there people who make 10 million a year? Yeah. Okay, so there's no upper bound. Okay. Okay, so, just for the sake of our chart, I'm going to write 1 million, okay? But we know that people make much more than $1 million a year, okay? So just from looking at this, what is this an indicator of? It's going to be right skewed, right? So if we create kind of our number line, we just go, if I go 0 and if I mark off 100,000 here, okay? And so we have 50,000 right there. Okay, so this would be 100, 200, 300, 400, 500, 600, 7. Okay, I'm not even going to be able to fit 1 million. Okay, so this is 800,000. Okay, so I'm just going to write 200, 300. So this is in thousands of dollars. Okay. Okay, so kind of your vast majority of people in the U.S. will be making between probably 50 and 150,000 or something like that. Okay, so this is going to be kind of like most everyone, and then you're not going to have very many. I mean, you do have some, but you're going to have very few. And then as you get further and further out, there are still people, but you just don't have that many people making over that much over 100-something thousand, right? So this is probably, our angle, I don't know, something like that, okay? Where it's still, if if somebody at a party says, you know, I make $150,000 a year, that still sounds impressive, okay? But on the, you know, the scheme of the number line, 150,000, that's on the low end, right? And then, you know, I mean, people complain about the 1%ers and whatever, you know, and I didn't even get to $1 million. This is 800,000, right? So, and we would say, you know, we've got a tail over here. This is definitely right skewed, okay? And as far as, you know, the lowest income that's possible, it's 0. You can't go lower than that, okay? And so that's what we have here, okay? So income in the U.S. is, and income, since money has been invented, has really been right skewed, okay? So income is right skewed. Yes?
So is the lesson here then to ask ourselves what is the typical?
Yeah, so the lesson is ask yourself what is typical, and if we can have outliers in the upper direction, the lower direction, or in both directions. Ask, can we go extremely high or extremely low? Do those values exist? Okay? If you have values extremely high but not extremely low, that's skewed right. If you have values extremely low but not extremely high, that's going to be skewed left. And if you have extreme values in both directions, that will be symmetric. Question? Yes?
So what if you like factor in debt? Like you could be that way you can go negative.
You can go negative, but then that's not an income. That's just like, that's a different thing, right? Like if you work, you can't be paid negative wages, okay? Then it's not allowed, yeah.
So let's say the general trend is right skewed, but then there's like one extreme left outlier. Does that still count as symmetrical?
Yeah, now you're getting in these off. I think we would have to look at the thing, and if it's like pretty much everybody except for one person fits skewed right, then it's probably better to call it skewed right. But look at the overall shape, okay? Yeah, these are just general shape terms, right? Like, you know, we have shapes we have terms to describe people and things like that, and the thing is like, there's always exceptions, right? There's always someone who's like, oh, well, you know, I don't know what. You go to the glasses store and they're like, do you have a square face or an oval face or a heart face? And it's like, well, I don't know. This is the face I look at. And, you know, so we try to have these terms and we try to say like, oh, this will fit your face well if you got a rectangle face. And you go, okay, well, thanks for the glasses. I don't know, right? So yeah, I just gave you 3 terms that fit a lot of things, but maybe not everything, okay? The other part that it explained was this idea of being unimodal, okay? So here, this is unimodal, meaning we've got one peak, okay? Over here, we could have something that looks like this, and we would call this bimodal. And then if you have more than 2, we generally just say multimodal, okay? But
what about try?
I mean, you can, but it's like saying, I did this once, I did this twice, I did it thrice. You could say that, but you just say I did it 3 times, right? Or so generally we just say this thing has 3 peaks, or if we wanted to use a word, we would just say multimodal, okay? But okay, so you know, if we think of as far as things that could be bimodal, I'm going to use a gender-based example here. So, this is all right. Whatever. Okay, so and I recognize that gender is is more complicated than just having two cases. But you know, if we looked across the board and we measured testosterone production in humans, okay? Everybody produces testosterone at some degree, okay? Everyone produces testosterone. Overall, though, if we were to graph it, okay, and this is a completely exaggerated graph, okay, it would look something like this, okay? And you'd have kind of your typical testosterone production for females, okay? And you'd have kind of your typical testosterone production for males overall, as you know. But you know, you've got people in between, and you could have females over on this side, and you could have males on this side. But overall, by and large, you're going to have something kind of like this, okay? If we measured how much, so keep in mind this is a numeric quantity, right? So you could measure testosterone production as far as like nanograms per deciliter or something like that, right? So measured as, or this is micrograms per deciliter or something. So this is an actual value for testosterone production. Okay, and so by and large, you're going to kind of get this general two-peaked thing, and you're going to have people in between, but for the most part, something kind of like that. Okay. If I ask generally, so students will often ask things about categorical things that we think of having two categories, like political opinions or things like that. Those would not work for being, whether it be bimodal or whatnot, because those are not numeric values, right? So all of this stuff, this represents numeric variables, okay? So talking about unimodal, bimodal, and all of that stuff only works for numeric variables and does not work for categorical ones, okay? Numeric variables only. Okay, is that okay? So, I mean, you might be able to find a proxy for something like political opinion and turn it into a number, right? So you might be able to say, on a scale of 0 to 100, you know, what is your rating of Donald Trump or something like that, okay? And you might get something that is bimodal, okay? Because you're either going to have people who like 95, 100, I love Donald Trump, okay? And you're going to get people who say like 0, 5, I hate Donald Trump, okay? And you're probably not going to get a whole lot of people that say, oh, 50-50, you know? I mean, I like, you know, you know, candidates like Donald Trump are, and even Hillary Clinton are quite divisive, okay? And so you're not going to have people kind of on the fence so much. And so you'll probably, if you said, on a scale of 0 to 100, what's your opinion of Donald Trump? You're probably going to get something bimodal, okay? But if you just said, like, are you Republican or Democrat or moderate, those would not work for being bimodal or something, because those are categorical. Okay, so you got to find a way to turn whatever it is that you're trying to get at into a numeric thing. Okay. All right. Does that make sense?
Yeah.
Okay. All right. So so those are describing our shapes. Okay. Yeah. Why don't we take a short break here? We'll say 5 to 10 minutes, and then we'll get started and we'll talk about numeric summaries here.